very nice problem. So the question says that for a function f from R to R, we define two sets AF and BF. AF is basically zeros of a function f on closed interval 0, 1, and BF is the zeros of the derivative of f from f on 0, 1. Okay, and we are taking all such differentiable functions, okay, that satisfies this condition that f of 0 equal to f of 1 equal to 0. That means f has at least two zeros at 0 and 1, and AF and BF are disjoint. Okay, we are taking all such differentiable functions. This is the collection. Then what can you say about this kind collection? Okay, so the options are given that there exists a AF in this collection such that AF is infinite. That means there exists some F such that there are infinitely many zeros of that F in closed interval 0, 1. Option 2 says that for all F is finite. Option C says that for all F, BF is finite. And option D says that there exists a F such that BF is empty. That means there exists a F such that the derivative doesn't have any zero. Okay. So let's try to solve the idea. So first observe. So if you have two zero, okay, say this one is a 0, say A, this one is B, okay, F has 0, so something like that. Then by mean value property, there must be a 0 of F prime, right? That means any two distinct zeros, if you choose any two distinct zeros, then there must be a zeros inside this, right? So in particular, if you can consider, say, a function which has distinct zeros, say 5 points, okay. So if you are considering some function which has distinct zeros, okay, say that these are the zeros, okay. Then it must have, the derivative must have a 0 at some point here, C1, here C2, here C3, here C4, like that, right? So this is the basic idea. So these questions is slightly interesting, okay. So you can do easily the option D. Option D says that there exists F such that BF is empty. It is not true, because see, given that f of 0 equal to f of 1 equal to 0, that means there exists C belongs to 0, 1 such that f prime C is 0. BF is always non-empty. That means this option is wrong actually. Now the question says that for all F belongs to this collection, AF is finite or not. So now I'm going to prove it, okay. Consider a sequence. Xn belongs to AF. That means you are considering a sequence of zeros of F on closed interval 0, 1, because AF is the collection of all points such that Fx equal to 0 and X belongs to closed interval 0, 1, right? Then by Bolzan-Weierstrass theorem, xn has a convergent subsequence. Okay. Let okay. Right, so 0 1 is closed, that implies that x belongs to 0 1, right? So that means xnk converges to x. There is a subsequence of zeros that converges to x. Okay. So by given condition, f of x and k is 0 because x and k are zeros of f, right? X, this will imply fx equal to 0. Then it will imply x belongs to x. Right? Now we are trying to find f prime x. So by definition, f prime x is limit n tends to infinity f of yn sorry right. So in particular, I can choose yn to be our x and k, right? Because x and k also converges to x. Then f dash x equal to limit n tends to infinity f of x and k minus fx by x and k minus x, which is 0, because f of x and k is also 0, fx is also 0, so it is always 0. So f prime x is 0. This will imply x belongs to pf. This will imply x belongs to af intersection f. But we already assume that the collection C contains all such f that satisfies this condition that af intersection bf is empty. Hence, find slightly many zeros in closed interval 0, 1. Okay. So that means this option is wrong. F cannot have infinitely many zeros. There doesn't exist any f such that af is infinite. That means for all f, af is a finite set. Now for all f, bf is a finite set. This may not be true. Can I find an example? I just give an idea how to construct it. So it is quite simple. So see, bf means it is derivative of zeros, right? So you can consider this kind of function. Say, just doing this, trying to make it flat and try to make constant in some small region, and then again come back and go to this. Say it is 0, this is 1. So here, say in a small interval, this is constant, f is constant. That means f prime is identically 0 on this interval. That means for every x here, f prime is 0. That means f prime has infinitely many zeros. but you can easily see that f has zeros only at 0 and 1. So f0 equal to f1 equal to 0, that condition also satisfied, as well as it is also satisfied that af and bf has non-empty intersection, because the zeros of f prime lies in between this. This is not a zeros of f prime. Okay, you can consider it in this way. So try to construct it. Okay, it's a very nice idea. But the main thing is that you have to prove that, and this is true for any closed bounded interval AB. So the general statement, let me write the general statement. For any differentiable functions on closed bounded interval AB, f and f prime has a common zero if f has infinitely many zeros. The same argument will work. Okay.